Hi! Have you ever seen a computer from the early 1900s? Perhaps you might be thinking about those huge machines, you know, the ones that appear in the old spy movies, the gigantic ones that occupy a whole room. Well, that's still fairly recent. I'm actually talking about something much older than that. Remember, 1 century ago. So go on, come on, give it a guess. As it turns out, the computers of the early 1900s were not whats, but who? Ah, interesting, right? Here's a picture. Look at that. Everyone in that room holds the job title of a computer. Oh, isn't that interesting? Now, just to give you some context, all these people, these computers in the room, they were computing performance bonuses for their organization. It's worth pointing out that the modern day motherboard and processor is modeled after this human organization. Why am I showing you this photo? Because I want to impress upon you that computational reasoning has very little to do with computers. It's a very particular way of thinking, a particular way of solving problems. Of course, nowadays we do a lot of this kind of thinking with a computer or a smartphone. But this mode of thinking has been around for a very, very long time. Now, archaeologists discovered a really fascinating device dating back to ancient Greece. They attributed its invention to, well, you call it Pythagoras, but do you know it's not pronounced Pythagoras? It's pronounced Pythagoras. That's right, it's the Pythagoras theorem. Anyway, they attributed the invention to Mr. Pythagoras. It's really cool. The device can compute the precise positioning of all the stars and planets in the sky. Now, to help you appreciate just how difficult that is, it's important to remember that in those days, the Earth was seen as the center of the universe. This meant that heavenly bodies didn't move in a circular fashion. No, they move in a loopy manner. So to be able to calculate the position, that's incredible, isn't it? Now, there are so many examples of computational problem solving across history and across various cultures. I won't go into detail, but I invite you to explore all of this on your own. It's very, very fascinating. The point I want to make in this course is that what we are looking at, what we are focused on, is a particular mode of thinking. That particular mode of problem solving. I want to cultivate in you a very special way of thinking, a way that can help you to solve problems better. Of course, we will use computers, but that's only as an aid to help you. So when I say compute or computation, I'm really just using the old sense of the word. Computation is the act of manipulating your inputs according to a set of instructions in order to achieve a desired outcome. Have you ever watched cooking videos or look at cooking recipes on YouTube? Those are actually instructions telling you how to manipulate your ingredients until you get the dish you want. Now, let me teach you a recipe that you can try on your own. Step 1. Buy raw papadums. I recommend the Taj Mahal brand. Step 2. Put a raw piece of papadum on a plate. Step 3. Put it in the microwave. Step 4. Microwave the papadum on high for 1 minute. Step 5. Press the stop button once the papadum has stopped fluffing up. Step 6. Enjoy the papadum. It's really crispy too. Now, with this recipe or instruction, you can now manipulate your raw papadum, your input, to get the desired outcome. Crispy, delicious papadums. Great, right? You don't even need a deep fryer. Now, so a lot of what we are going to do is to work backwards and figure out the steps or the algorithms needed to solve complex problems. But wait, doesn't this mean that everything is potentially computable? Well, technically yes. It seems that everything can be expressed as a set of instructions on paper or as code for a computer. So if you can write it out clearly as a set of instructions, then yes, it is computable. But not everything that can be computed well. Take friendship for example. You could write a set of detailed instructions on how to make a friend. You know, hello, smile, you know. But it won't guarantee success. You might even just get awkward smiles or worse, awkward silence. There are two classes of problems that cannot be computed well. The first are problems where the end result is just so vague and ambiguous it's hard to come to a concrete definition of what exactly we want to achieve. Take happiness for example. What does it mean to be happy? A life of pleasure? What sort of pleasure? How about a meaningful life? What counts as meaningful to you? How about a life free from sorrow and suffering? Does boredom count as suffering? But every time we attempt to define something, we have more questions than answers. If we can't come to a concrete definition about the end result, well, we can't come up with instructions to achieve it. But suppose that you succeeded in coming up with a concrete definition of happiness that's very clear, free from all vagueness and ambiguity, and people all around you can agree on what happiness is. Can the same instruction guarantee happiness for others? Well, no. We have different personalities, different tastes, so what works for you may not work for me. This is the second class of problems. 2, which is what we call intractable problems. The nature of the problem is so wide, so varied, that it's hard to arrive at a general solution that works well for many people. So when it comes to solving problems in this course, we'll focus more on problems that are clearly computable. Of course, we'll go into grey areas from time to time, and that's important for us because we'll need to examine the computational, social and ethical problems that arise from them. But here's a question. How do we create those sets of instructions? To be able to do that, we need to tap into a different skill set. The act of computation is merely an act of following a set of instructions. Crafting instructions, on the other hand, is an art known as computational thinking. It refers to a specific mental process of formulating a problem and expressing its solution in a way that a human being or machine can effectively carry out. Have you ever had someone give you instructions so bad and so unclear, you're not sure what you're supposed to do, you're so confused and blur, right? Well, the truth is, we all struggle to give clear instructions. It's hard. And that's because the act of developing instructions involves backwards reasoning. We know the end result, and now we have to figure out the steps needed to get it. That's not something we do all the time, and so it takes some getting used to. So it'll take a while to get used to this direction of thinking. It may be a bit of a struggle at the start, but let me assure you, it'll get better in the weeks to come, and by the end of this course, you'll be very proficient in it. Now, to get us started, I want to introduce you to 4 central pillars of computational thinking. You'll find that we'll use these pillars throughout the entire process of problem solving. Now let me tell you a story. Have you heard of the story of the famous composer Wolfgang Amadeus Mozart? After he died, he was buried in St. Marx's Cemetery in Vienna. Now at night, people could hear music eerily echoing in the cemetery. Now one of the musicians who worked very closely with Mozart recognized the music. It was Eine kleine Nachtmusik, but it was playing in reverse. Mozart was decomposing. Yes, so our first pillar is decomposition. This comes in when we are trying to develop a solution. Do you remember back in secondary school or junior college, your teacher might have taught you, when you write an essay, you must plan an outline. Actually, when you're planning an outline, you are carrying out the process of decomposition, right? You write an intro, then you write about A, write about B, write about C, then you write a conclusion. That is decomposition. It's essentially a task of outlining exactly what we need to do to achieve that task, right? Let's move on to the next pillar. Have you ever entered a very messy room? There's clothes all over the place, papers and books scattered all over the tables, the chair, the floor, there's socks on the top of your window for whatever reason, right? Have you ever paused and asked yourself, how is it that I'm able to look at all these things and still be able to recognize the table, the chair, and the window despite all the mess in the room? Yeah? That's because you're applying the second pillar of computational thinking, which is pattern recognition. You remember the pattern of a table, you remember the pattern of a chair, the pattern of a window. When you look at this ball of mess known as the room, you are able to recognize those patterns. But what helps you recognize those patterns? That's because we're applying the third pillar of computational thinking, abstraction. We see a huge mess, but at the same time, we are able to ignore all the mess. We are abstracting, stripping away all the messy details until we see only what we need to see: the table, the chair, the window. Now, our last pillar is algorithm design, creating those step-by-step instructions or recipes for problem solving. I already gave you the example of a recipe for making papadums in the microwave, so that's an algorithm. Ta-da! It's easy, but starting out can be a bit of a challenge. So don't worry, we'll go slow and steadily, right? We'll learn to master the art of algorithm design in the weeks to come. Of course, you might say, hey, these 4 pillars seem rather commonsensical, so why bother? Well, here's the thing. These 4 thinking processes are part of our intuition. Yeah? If we don't do anything about them, then we can't use those intuitions to effectively solve problems. So what I hope to do with you in this course is to help you sharpen those intuitions so that you can become really good at applying computational thinking processes when it comes to problem solving. So I'll see you in the next video.